Hello, let's do a homework problem from section 6.8. This is problem number 10. Here we have a vector field, the velocity field of a fluid that's given by V, and they want us to compute the flux of V across the surface, and we can call it surface S. So they want us to compute the flux of the vector field. So this is a double integral over the surface S, or this is your surface S, of the vector field V, and the flux is associated with a VDS, which means we need some way to parameterize and all that. But they want us to use the divergence theorem. So the divergence theorem says that this is actually equal to the triple integral of B of the div of V dV. Now, there's one stipulation, there's a few, but there's one really important one, in that S is closed and it's the boundary of B. So that's how we would identify B. Now, if we take a look at this surface, just by guessing, the surface has an x squared and a z squared, and the y is not squared. So this is looking like a paraboloid going along the y-axis. And furthermore, if we bring the z and the x over to the other side, we're going to have a 9 minus x squared minus z squared. So that would actually look like a paraboloid opening up along the y-axis. Well, opening up going to the negative y-axis. We start off at 9 here, and then it'll close in on itself on the x and the z, and it looks like it'll stop here because they want y to be bigger than 0. All right. If we talk about the orientation, going away from the origin, it'll look something like this. So these are going to be your normal vectors. Now, this does not look like, unfortunately, this does not look like a closed surface. It looks like it has a boundary and it is open towards this place over here. So we have an issue about S being closed. So we have an issue about S being closed, and it's not. What we can do is we can close it. We can close it with any surface that would close this up. And the simplest surface that seems like it would close this up would be a disk. So let's close this up with a disk. Let's call this disk S2 to describe it as a surface. And we didn't talk about the intersection, but if we take a look at the intersection here, it'll be x squared plus z squared is equal to 9. That's when y is equal to 0. So the S surface, there's going to be several ways to describe the S surface, but we'll describe S2 as the disk x squared plus z squared is less than or equal to 9, which is 3 squared. So we know that has a radius 3, and this is in 3 dimensions, so we have to specify that y is equal to 0 in this case. So that describes that disk. Okay, we can parameterize this in several ways, but let us just set up how we're going to use our divergence theorem. So this is not closed, but if we close it up by adding S2, then we can have S2 and the original S. This is what we're going to be solving for eventually. And this is equal to the div, the triple integral of the div of v over b. Again, this is what we're interested in solving for, and so we can just solve for that here algebraically. So this triple integral, or this flux integral that we're looking for, is equal to the triple integral over b of the div of the vector field minus this added on flux integral from the surface. All right. All right. So let us find each of these components. Let's find the triple integral, and then let's find the flux of that other one. Let's do the triple integral first. So we need the div of v. And v is equal to this, so let's take the derivative with respect to x. For the first one, it's going to be x squared, 3x squared, cosine z is constant. And we want to add the derivative of the second one with respect to y. So that's 0, and then we have a minus 3x squared cosine z. Ooh, that looks like that'll cancel. And then, oops, we're not done yet. We need to take the derivative of this with respect to y. That's going to be minus 3z squared sine x. And then we take the derivative of the last one with respect to z. It's going to be plus 3z squared sine x. Well, so they would cancel. I've got a couple of terms that would cancel itself out, so this will end up being 0. Well, if the div is equal to 0, then certainly the triple integral of 0 will equal to 0. So that means this thing has no contribution, it has 0. Which means this flux integral that we're actually looking for should actually be equal to this, this flux integral. All right, with a negative. So let's figure that out. So let's say minus, let's put the minus in later, and S2 of V ds. All right, what do we know about this particular surface? It is a surface that is flat, and if we're following this outward going normal vector, we're going to have a normal vector that goes outward, which means it's going along the negative y direction. So it looks like our normal vector is going to be negative y. Oops, let's call it negative j. And that would be 0, -1, 0. All right, and we are dealing with a flat space, so we can rewrite our integral, our flux integral, as v dotted with your normal vector ds, and this s this time is without the arrow. And how do you find that s? It's the magnitude of the magnitude of the cross product of the derivatives of the parameterization, which is essentially the normal. And so we can go through a little bit of that process. I kind of don't want to get too bogged down with that computation, but let's see. We can say that this parameterization will be an R of, and the independent variables here are going to be x and z. So we can put R, x, z. Let's make this a little bit bigger, focus on this a little bit more. And this is going to be x in the x and z in the z, but then the y is equal to 0. And we can imagine this as your function of x and z. And then we can follow through the procedures of the graph parameterization where this would be the r x cross r z vector will be the derivative of f with respect to x, comma, -1, comma, the derivative of f with respect to z. But the derivative of f with respect to x and the derivative of f with respect to z are 0 because the function f itself is 0. So 0, -1, 0. And the ds without the arrow on it is the magnitude. So the magnitude of this is just going to be 1. So our ds will just be 1 times dA. And A is the domain, or the domain here. This is also the domain. So on the xz plane, the shadow, which is exactly what the surface is going to be your domain. All right? Okay, so let us rewrite our flux integral into a regular double integral over the domain. We didn't complete this cross product, but let's do it now. The V is this big mess, but we're only going to be concerned about the middle term, which is going to be 4 minus 3x squared y cosine z minus 3 y z squared sine x. And then the third component won't matter because when we take the dot product, we will get rid of those anyways. Not only that, but if we look at our parameterization, remember that x is equal to x, z is equal to z, but y is equal to 0. So if y is equal to 0, we have a couple of places where the y's exist, and so those are going to disappear. So we really just have 4 times -1. And so when we take the dot product here, this will be the double integral of 4, or 0, it'll be 0 times plus 4 times -1 plus 0 again, and then dA. And now we're going to use some more information. If you remember back from chapter 5 with double integrals, we have -4 times the double integral of 1 times dA, and this is just equal to the area d. What is d? D, remember, was the circle or radius, circle of radius 3. And so it's going to be -4 times pi r squared. So that's -36 pi. All right. So that's this integral, and then there's another negative in front, so that would make that positive. So then finally, we can say this is equal to 0 minus -36 pi, which will give us a positive 36 pi. So then our flux of the surface, that paraboloid of your vector field V ds, will be positive because we have a 0 minus -36 pi. Okay. All right. That's a problem. I hope that helps. Good luck.